So in today's lesson, we're going to be learning about wave characteristics. So basically just different terminology that we use in conjunction with waves and processes that waves experience. So first we're going to start with geometric wave characteristics. Well, the term geometry or geometric usually refers to shapes, and so we can think of it as sort of describing aspects related to the shape of the wave itself. So let's start with off with a fairly simple one. The wave we can characterize as having these high points and then these low points. These high points and then these low points. The high points have a name, and they're called crests. So here I have a crest. This is a crest, and here's another crest. So in the same way, these low points have a name as well, and they're called troughs. So here's a trough, exclamation mark, and here's another trough. Okay, next term that's important to know. Let me get rid of some of these. So if I were to look at the distance from this sort of 0 point, which by the way is the equilibrium point, that's sort of like the rest position for the wave. Then if we measured the distance from that equilibrium point all the way to the highest peak or the lowest trough, that right there represents the amplitude, which has the symbol A. So that's my amplitude of my wave. So another term that you need to know is, which I would say is probably arguably one of the most important, and it is wavelength. And so wavelength has this symbol lambda. So I'm going to put that in quotation marks. It's pronounced lambda, and it's just the Greek letter lambda. Sort of looks like almost like an upside down Y, sort of. And so a wavelength can be measured in different ways. I'm going to remind you of our pendulum. Remember when we had that pendulum? And so here's my pendulum, and I can describe its motion. So, and of course, you know, right here it's resting, so this is what we would call its equilibrium position. But then that pendulum, of course, if we raise it, it's going to have an amplitude, and so it's going to swing out and then back. So that's sort of like it starting at its rest position, swinging out and then back. And then it's going to continue in the opposite direction. So then it's going to carry on in the opposite direction and then return back to its equilibrium position. So that is like it going here and then back. So one complete cycle is essentially it's out and back, out and back. And so on the graph, that shows up as out and back here. And so that represents a wavelength. That's one way that we can sort of describe our lambda. So here to here, boom, that would be a lambda. Another way to measure it, if I were to take this line and transpose it to another position, another place I could put it where it would also measure a wavelength would be crest to crest. So here to here, this is also a lambda. As you would expect, I could also measure a lambda from trough to trough. So all of those are ways that I can measure wavelength. Now I'm expecting that some of these terms should be somewhat familiar to you based on a math class that you'd have taken. So the next one is a phase shift. So phase shift is basically just a horizontal translation. You're just taking that wave and you're moving it sideways a little bit so that it's just identical in shape, right? So here I can see that I have an identical shape, the blue and the red, but that there's just a discrepancy in their horizontal position. So that we call a phase shift. So we can also talk about waves being in phase with each other or out of phase with each other. So really, these two first graphs right here are showing two waves that are in phase with one another. In fact, really, it was hard to see with the one picture, but really you can see that there's like a blue line and a red line exactly on top of each other, and ideally that's really what I should show for in phase. So it's kind of making like a purpley color. And so those waves are completely in phase. If I were to superimpose this wave on top of this one, then they would blend together. So waves can also be out of phase. So I can see here there's a phase shift that's happened. If I'm considering the blue wavelength, or the blue wave rather, to be my original wave, then it seems as though it's been phase shifted fairly significantly here, but so that the waves are no longer considered to be in phase. They're out of phase. I could also describe the waves as being completely out of phase, like you see in this last diagram here. And here you can see that essentially these two waves would cancel each other out. I have, the one blue wave's crest aligned with the pink wave's trough, and so those would completely cancel each other out, and they would be considered completely out of phase. So the next thing I want to discuss are some time-based characteristics. So time-based characteristics, we're no longer looking at the shape per se, as much as what is going on with the wave in its motion. Let's start with the definition for frequency. Well, frequency, I think you intuitively have an understanding of, it's sort of like a measure of speed in a way, right? So frequency by definition in physics would be measured by the number of cycles, or the number of wavelengths in a given amount of time. So let's take a look at these two waves that I have here on the bottom. So I have my red wave and I have my blue wave, and so I'm going to say, well, let this be time 0. So this would be t equals 0. And I'm going to consider over here to be maybe time 1 second. So if I were to look at the frequency of my red wave, I can see that in that same time period, I have a far greater number of wavelengths or cycles, right? See, I have, here's 1, 2, 3, and a bit. So, my frequency in that 1 second time period would be 3 and a bit per second. So the unit that I use, cycles per second, is really what we refer to by definition as a hertz. So the unit for frequency would be the hertz. Whereas I can see in my blue wave here, I have 1, 2 wavelengths. So, and we can see that visually, right? The greater number of crests and troughs indicate that it's a higher frequency wave, but we can also calculate that mathematically, but if we have some values, some quantitative data. Now, another related term is period. So the period describes the time it takes for one complete cycle, or one wavelength is usually what we're referring to. So, for instance, if I were to compare the period of these two wavelengths, I'm going to start at the beginning of one wavelength, and this seems like a good place to start, right? And I want to know how long it takes for one complete wavelength to complete. So if I look at my red wave, I'm going to go down and then up again. So one wavelength takes whatever that amount of time would be if I were measuring it. Okay. And let me look at my blue wave for a second here. I'm going to use maybe the red for that, maybe the black. So if I look at my blue wave here, I go from here all the way up and then back down again. So you can see that it would take a little bit longer for it to complete a single cycle. So let's think about that. I said the red wave, okay, the red had high frequency, but it had low period. Okay, and the symbol for period is a T for some reason. And if I look at the blue wave has low frequency, right? But it has a high period or a high period value, right? It takes longer for it to complete a complete cycle. And so I've just outlined for you that period and frequency really are related. They're simply sort of almost opposites. They're reciprocals. So let's look at that mathematically. So if writing a reciprocal relationship involves saying, okay, well, one is equal to the other one, but flipped, right? So another way to write this would be that frequency is equal to the period to the power of -1. And if I were to, put the two equations for frequency and period side by side, then I would see that. So if frequency is equal to the number of cycles per unit time, and period is equal to the time per cycle, which I get by dividing by the number of cycles in a given amount of time, I can see clearly that they are simply reciprocals of each other. So hopefully you've been able to make sense of these concepts. Many of them I'm hoping are quite familiar to you based on exposure in math class. Here are some questions that I would like you to try for homework to get you familiarized or more comfortable with these terms so that we can use them in regular conversation without there being much confusion. Page 387, numbers 1 to 6.